Hello. Now we continue our work with section 10.1. We shall consider examples where from given image we have to find its original. Given is the image, find the original. We did last time up to number 22. We continue with 24. Here is number 24. We are given this image, big F is S negative 3/2 power. We can write 1 over S 3/2. In this work we use extensively the table which I mentioned on page 562, and we shall read in the table from right to left. Searching in the right column, we have to find image which has a denominator with such structure, and there is only one entry in this table that can be compared to this, so we can use Laplace transform t power a, which will be gamma a plus 1 over s power a plus 1. We had to use this entry. No other entry has such a denominator. Comparing the denominators, we see that 3/2 should be a plus 1. So from here we compute a is just 1/2. A plus 1 has 3/2. And now we write our formula, this one here, for this particular a. We write Laplace t power 1/2 will be gamma 1/2 plus 1 over s 1/2 plus 1. This will be 1/2 gamma 1/2 over s 3/2. We have to be prepared with the gamma function. From its properties, we know that gamma 1/2 is root of pi. So we write here 1/2 root of pi over s 3/2. I shall rewrite this here again. Laplace t power 1/2 equals root of pi over 2, separately 1 over s 3/2. Our image stands here. This is our big F. Now I shall solve for this big F. From this equation, 1 over s 3/2 will be 2 over root of pi or plus t 1/2 power. The constant 2 over root of pi I can bring inside L, property of the Laplace transform, so I can write this Laplace 2 over root of pi times t 1/2. So the big F is written this way. And the big F is Laplace transform of the small f. So what stands here inside the brace is our small f. This is our original. Here the answer is f small t is 2 over root of pi t power 1/2. So we found the original. Okay, moving further. Next example is 26. We are given big F, which is 1 over s plus 5. Again, searching in the table, from the table, we can find only one entry where the denominator has such structure, and this is the Laplace transform of the exponential function. Laplace e at is 1 over s minus a. Again, comparing denominators, we identify s plus 5 should be s minus a, so a should be negative 5. We write again the formula, this one here, with a negative 5. Laplace exponential negative 5t will be 1 over s plus 5, exactly what we need. That's our big F. So the small f is inside L. The small f will be exponential minus 5t. That's the original. Done with 26. Moving to 28. We are given big Fs, 3s plus 1 over s squared plus 4. Again, we carefully search in the table, trying to identify entries with similar denominators. The denominator is important. There are two entries where we have sums of squares in the denominator. Let me write them here. In table we find Laplace cosine kt. This is s over s squared plus k squared. K is a coefficient. And we also have Laplace sine kt equals k s squared plus k squared. No other entry has sums of squares in the denominator. Comparing these denominators in our big F and this in the formulas, we see that k squared should be 4, so k is 2. We write again the two formulas for this particular k equals 2. This will be Laplace cosine 2t s over s squared plus 4. Laplace sine 2t is 2 on the top s squared plus 4. And now we're coming closer and closer to our big F. Our big F on the top has two terms. We have to break it in two parts. So I'm writing the big F, which is 3s plus 1 s squared plus 4, 3 times s squared plus 4 plus 1 time s squared plus 4. The first term resembles very much Laplace transform cosine 2t, but we have this 3 in front. The second, so I shall write 3 in front like that, s squared plus 4. For the second, it resembles the transform of the sine. We associate these two, but we need 2 on the top. So we shall put 2 on the top and divide by 2 for compensation. Write it this way. So the big F now is written 3 times Laplace cosine 2t plus 1/2 Laplace sine 2t. Using the properties of the Laplace transform, we shall collect everything in one single L. So we shall write this Laplace transform 3 times cosine 2t plus 1/2 sine 2t. And looking inside the braces, we find our original. So Laplace of something equals our big F. This something has to be the original. Here is the original. 3 times cosine 2t plus 1/2 sine 2t. We don't have to use notations like L minus first. No need to use such notations. Our technique is this. The method is this. The big F that is given, we write the big F, we try to write in the form Laplace of something. And this something is our f of t. All the time we do this. Moving to number 30. I'm doing the even numbers. You'll do for homework the odd numbers. In number 30 we have big F, which is 9 plus 1, 4 minus s squared. Again, searching in the table, we can find two entries where the denominator has such structure, and these are Laplace of hyperbolic cosine kt is s over s squared minus k squared. Laplace transform hyperbolic sine kt is k on top, s squared minus k squared. Again, comparing the denominators, we see that k should be 2. And I'm writing, for this particular case, the transforms, the formulas. Laplace cosine hyperbolic 2t s over s squared minus 4. Laplace hyperbolic sine 2t is 2 on top, s squared minus 4. Minus 4. Our big F we shall decompose again. The big F that we have, we write 9 over, I'm sorry, correction. In the big F, it's 9 plus s. 9 plus s. 4 minus s squared. We break this way 9 over 4 minus s squared plus s over 4 minus s squared. The difference of squares in the denominator comes here in reverse order, so we change the sign. Multiply top and bottom by -1. We can write -9 over s squared minus 4, and here negative in front, s squared minus 4. The second term is exactly Laplace transform of sine hyperbolic. Laplace transform of cosine hyperbolic. For the first, we need 2 on top, not 9. So again, I'm writing this way, dividing by 2 and putting 2 on top, s squared minus 4 and minus s squared minus 4. And these are exactly our formulas. We have -9 halves Laplace of sine hyperbolic 2t minus Laplace cosine hyperbolic 2t. Collecting everything inside L, this will be Laplace transform -9 halves sine hyperbolic 2t minus cosine hyperbolic 2t. And looking inside the braces, we find our original. This will be -9 halves sine hyperbolic 2t minus cosine hyperbolic 2t. And that's it. Next one is 32. The big F looks strange. It's 2 times exponential -3s over s. What is the small f? Well, to solve this problem, we need to use the last entry from the table. It's a special function called step function. And now I'm introducing this function here. Here is the definition. U t minus a, where a is some non-negative number, is defined to be 0 when t is between 0 and a, and is defined to be 1 when t is greater or equal to a. This is our step function. You can see this definition on page 562. Now, what is important for us, the Laplace transform of the step function of plus u t minus a is exponential negative as over s. And we can recognize this expression here immediately. Comparing these two, we see that a should be 3, so that 2 times exponential negative 3s over s, I can write like 2 times Laplace u t minus 3. Bringing 2 inside, this will be Laplace 2 times u t minus 3. And here is our original f of t. So f of t here will be 2 times u t minus 3. How do I know that the Laplace transform of u is this? Using the definition of Laplace transform, let me write this definition again. Laplace ft equals integral 0 infinity ft exponential minus st dt. If I put here the step function u, Laplace u t minus a, this will be integral 0 infinity u t minus a exponential minus st dt. Remembering the definition of u, we see that it's good to break this integral in 2 parts, from 0 to a and from a to infinity. The first will be 0 because u is 0 between 0 and a. So the integral becomes from a to infinity, just integrating 1 exponential minus st dt. We can solve it. Here's the antiderivative from a to infinity. So we take limit to infinity, and we have done this several times. Limit to infinity of this function will be 0, and this will be then 0 minus the value at a, which will be exponential minus as, negative s. 2 negatives make it positive. And that's how we compute the Laplace image of the step function. Okay, enough examples for today. Here is your homework. And this is homework part 2, inversion, for section 10.1. You do examples 23, 25, 27, 29, and 31. Bye for now.